Last time we saw that para-unitary polyphase matrices are an easy way to obtain the inverse polyphase matrix for the synthesis. We just need to transpose the matrix and replace z by z to the power of -1. But how do we obtain useful para-unitary polyphase matrices or filter banks, more useful than a simple transform matrix? We now need to go one step further in increasing the length of our polynomials in the polyphase matrix. We saw that the zeroth order polynomials result in our usual transform matrices like a DCT, but we already know their frequency response are often not good enough. The next step is to look at polynomials of first order, where we have elements of z to the power of -1. Then this leads to impulse response with a length of two blocks. The first block corresponds to a delay of z to the power of 0, and the second block to the z to the power of -1. Hence, we get the impulse response length of L equals to 2n, with n the block length and the number of subbands. One widespread example are the so-called MDCT, the modified discrete cosine transform filter banks, which are so-called cosine modulated filter banks. As we saw in lecture 6, modulation means the multiplication of a baseband prototype filter impulse response with a periodic modulation function, here a cosine function. In this way, all the subband filters are obtained from one prototype filter h of n. In this case, for the analysis filter bank, filters are given here, this equation 1. And we have that the k goes from 0 to n-1, and here are the subbands, and the time index n goes from 0 to 2n-1, meaning we have filter length with length L equals to 2n. The prototype filter h of n is a low-pass filter, and the cosine function is the cosine modulation function that shifts the center frequency of the filter to the cosine function frequencies, given by pi divided by capital N times k plus 0.5, such that we evenly cover the entire frequency range from 0 to pi. Imagine the low pass having a pass band from a minus pi divided by 2 times capital N to pi divided by 2 times capital N. Then the first subband, or the subband for when k is equals to 0, already results from modulation with frequency pi divided by 2 times capital N, and hence it goes on the positive side from 0 to pi divided by n. In this way, we obtain n filter of passband width pi divided by capital N, which then cover the entire frequency range between 0 and pi in the positive frequency range. The negative frequencies are the mirrored version. Observe that we can view in equation 1, again here, the multiplication of h of n with the cosine term also as a window design method. So we can see this multiplication like we've seen before with the window design method. Here, the ideal filter would not be a sinc function, but an infinitely long cosine function. This corresponds to infinitely narrow bandpass filters at the cosine frequencies as ideal filters. After windowing, they then become wider. Because of these two different views, we see two different names in literature for this h of n. It could be a baseband prototype, but we also see as a window function. It's a time-reversed baseband prototype.